The next three tests all concern simply supported beams of varying slenderness. A central vertical load, causing bending, is increased to failure in each case. The first beam is just over a metre in length and can be described as being short and stocky. The load is applied to the beam by a screw jack device via a vertical rod. During the loading of this beam, here shown accelerated, deformations are confined principally to the vertical plane, with failure occurring essentially due to the attainment of a plastic hinge at the point of maximum moment. On removal of the load, permanent deformation remains. The second beam is 7 metres long and is much more slender. The load is applied as in the previous test. Observe the response, shown again in an accelerated manner. It can be seen that significant lateral deformation and twisting occur, in addition to the in-plane bending displacement. This is known as lateral torsional instability. The direction of the lateral movement is determined by the initial imperfections present in the unloaded beam. When the beam is unloaded, full recovery occurs, with the beam returning to its original undistorted shape. No permanent damage has been done to the beam, which demonstrates that the failure is elastic in nature and is due to instability. For the analytically straightforward case of a simply supported beam subject to a uniform moment m, using small deflection theory, the equation for the value of the critical moment mcr causing instability is as shown. EIY is the minor axis flexural rigidity, GJ is the torsional rigidity, and L is the length of the beam. Note the coupled nature of the lateral flexural and the torsional rigidities and the absence of major axis properties. For a very stocky beam, the plastic moment is significantly less than the critical moment, and instability does not occur. For a very slender beam, the reverse is true, and the beam will fail by elastic instability. The response of very stocky and very slender beams is quite clearly defined, and relatively simple to analyse, at least in an approximate manner. However, many practical unrestrained beams lie in the intermediate slenderness range, where the effects of elastic instability and plasticity interact. The third beam of this series of tests is just over 2 metres in length, and is neither very stocky nor slender. The beam is subject to load as before. It can be seen that lateral deformation and twisting occur, together with plasticity. Removal of the load is accompanied by only partial recovery of deflection, and significant permanent bending remains in both principal planes. Consider the following plot. The vertical axis is material bending strength, PB, in newtons per millimetre squared. The horizontal axis is lambda LT, which may be thought of as a lateral torsional slenderness. Clearly, for steel which has a design yield strength of 275 newton per millimetre squared, this value represents a limit beyond which the material may not be used whatever the slenderness. Conversely, whatever the material yield strength, the beam can still fail by lateral torsional instability. In terms of extreme fibre stress, this behaviour plots as a line which has a very low value when the slenderness is high, but has a very high value when the slenderness is low. This line too is an upper bound to the actual bending strength. For low slenderness material, strength is the limiting condition, but for intermediate values of lateral torsional slenderness, where plasticity and instability interact, the values of design strength represent a realistic, safe solution, with the reduced material bending strength being lower than the yield strength and also below the instability curve. There are other actions which are involved in the instability of beams. One of these is warping. For steel beams, actual warping deformations are very small and are barely visible, but they may be seen using the soft rubber model. This short beam is being subject to equal and opposite end couples, and torsion occurs. However, in addition to the primary twisting action, it can be seen that the end cross-sections no longer remain plane, but the elements of the cross-section distort out of the plane perpendicular to the longitudinal axis of the beam. This phenomenon is known as warping. In this example, warping is free to occur, and the equation for the critical moment given earlier is valid. However, if axial movement is restrained so that warping is prevented, as is often the case in practice, then this equation is modified by the addition of an extra term. The moment corresponding to instability is now enhanced by being multiplied by a factor which is always greater than or equal to 1. The warping component of the instability moment contains a term which is related to the warping resistance EIW and the torsional rigidity GJ of the beam. Note that when L is large, the term in the second square root tends to unity, showing that warping is only important for beams of modest length. This reflects the relative importance of warping. Observe the response of the two cantilever beams which are of equal length and which have nearly equal major axis flexural rigidities. The one on the left has a high minor axis stiffness, whilst the one on the right has a low minor axis stiffness. Initially, as equal load is applied to each beam, their behaviours are almost identical. However, for the beam with low minor axis stiffness, as loading progresses, instability intervenes. The cantilever on the left does not suffer any instability and would eventually fail by plastic action. Lateral torsional buckling is only likely when a section has significantly different values of second moment of area and is subjected to bending in the stronger plane.